Okay, welcome to session 15 of the course on mathematical signal processing. We're in the beginning of the 8th week, and we have done so far quite a bit of functional analysis. You have seen a number of function spaces, and I understand that this might be a difficulty for engineers who are not used to functional analysis. I tried to explain that the use of infinite dimensional function spaces, which means for me the use of function spaces which have norms which allow to do approximation to describe convergence to form series infinite sums, so to say, in a good way, is important and can be done without using a particular basis. We will not have enough time in this course to describe operators by infinite matrices or maybe by integral kernels. The Fourier transform is a prototypical example of such an integral transform where you can think that a sequence or family of Diracs at all the points is a continuous orthonormal basis. Well, kind of, and it's one of the challenging things to make it intuitive, but also mathematically correct. So let me start our session today with summarizing from the extra script in the current version of November 3rd, the things that we have done already so far. The lemma 29, which we have on the screen, states that if you take a nice function which has integral 1 and you apply it to a nice other function k by compressing it, str is the area preserving compression, you will observe pointwise convergence, actually uniform convergence, because the support of the compressed G is shrinking, the K has fixed support, so everything is happening in a box. Now we have our functional analytic principles that allow to say, well, if you have two guys, the G and the K, and you apply a bunch of operators, then you can transfer from the dense subset in L1 to all the elements. Here we have the extra probability problem that an approximation of G by a function with compact support may not have exactly integral 1, so you also have to take that in the limit, but you get that you have for any f in L1 and any G in L1 with area integral 1, and that's just the extended integral, you get the limit relationship that they act almost as if there were a unit. So recall, we do not have a unit in the algebra L1 because it would mean that on the Fourier transform side, the unit would have to be constant 1. And constant 1 is not a function decaying at infinity, but the Riemann-Lebesgue lemma tells us that we have Fourier transform also always decays at infinity. So there is no true one, and we know, of course, from the bounded measures, you would take the delta at 0, and so essentially it's a statement delta 0 is not an element of L1, which means it cannot be approximated in the norm by nice functions having a density. Okay, now here is one of my many pictures I'm producing more and more about the relative situation of the different function spaces. You see here the blue object is the L1 symbol rotating by 90 degrees, and we will explain this more by looking at spectrograms. That's in future section. Corresponds to taking the Fourier transform is 90 degrees. So the red object in this picture is the Fourier algebra. The range of all the Fourier transforms now taken in the sense of bounded measures of all the L1 functions. So this is an algebra of functions inside of C0. That's why we put it, the red rhomb inside the green box. Now, I'm not going through the technical details, but repeat my outlook. We're going to the nice situation of this Banach-Gelfand triple, consisting of the algebra S0, the Siegel algebra S0, the dual space, the Hilbert space L2 in the middle, and the dual space is 0 prime. So we will start to make use of a 0 prime, the so-called space of mild distribution, as I called it since a few months, in the rest of the section. Now, in the process of doing so, we had to prove the Fourier inversion theorem, which means we had to look at the functions which are integrable, so that we have a forward Fourier transform and an inversion formula. And this is in this picture depicted by the red symbol, which, as you can see, is behaving locally like the Fourier algebra. This is the strong restriction, globally like L1, and it's Fourier invariant. You can rotate the red object by 90 degrees. Inside of this, we have the Wiener algebra intersected with the Fourier transform of the Wiener algebra. This is where Poisson's formula, that's one of the topics today, will be valid. I have changed the symbol here, so here it's a simple square object. Now, in the picture, let's say the proof of this approximate unit, you see a typical situation that you're applying S0. Here we don't apply the abstract principle, but we did it in detail. Apply the compression to a function g in L1 and then convolve it with f. And then you say, well, if this was a nice function, then everything would be fine. So you're changing from the g to the k, where you can apply this procedure. And at the end, you have to go back. You get the k approximation, which has a slightly deviation from 1, and go back to the f, to the function f. So this is a typical example of how we use these abstract principles. Now, we have seen that you can use the sinc square function as the Fourier transform of the triangular function. So we can change the role once we have verified the inversion theorem, and can take the sinc square function as approximate unit. That means on the Fourier transform side, you're approximating by multiplying with a dilated, stretched triangular function, which gives a compact support on the Fourier transform side. So this approximate unit stuff, by choosing G appropriately with a band-limited approximate unit, so to say, you're verifying that the band-limited functions, the one which have a compact supported Fourier transform, are dense in the L1 norm. They are actually contained in any so-called Siegel algebra, but this is not the subject of my current discussion. Unfortunately, I have to scroll down. So here you see we had these abstract principles. I will not repeat this again. Maybe I recall to you that there is another important thing. No, this is also not relevant. Yeah, maybe I recall to you that we have defined a Fourier transform for bounded measures, and that the fundamental relationship for the Fourier transform, which is a double integral interpreted in two different ways, can be also put in the setting of measures. And yeah, this principle is something that I may not have explained in enough detail, but I will use it probably today. That is a statement about small spaces have large dual spaces. Well, this is not true as such a statement, but it's true if you're having the typical situation that we meet very often. If you have a Banach space, or actually a normed space, which is densely contained in the big space. So B2 is made such that any element here can be approximated by an element from the lower small space here. Now, a linear functional on this space has to be continuous with respect to the one norm, whereas a linear functional is called an element of the dual space if it's continuous with the other norm. And of course, we assume that the embedding of one by the other is continuous, which means that the small space has a more sensitive norm. So you can control convergence in the big space, which is kind of more loose, by convergence in the small space. But of course, you expect that it's a really larger space, so there is not an equivalence of norms. And the statement is, then every functional from the big space can be viewed as a functional in a small space. What looks trivial is almost trivial in the sense that the first part just gives you, you're starting with the continuous embedding, therefore anything which can be controlled by the B2 norm up to another constant can be controlled by the B1 norm of the function f. So I'm just using the embedding and the definition of a functional, and thus you get a continuous functional. But in order to have an embedding, you have to say, well, a functional which is, two functionals which are different have to be different. And then you need the density and you apply a limit relationship. Essentially what you're saying here is, if functionals sigma 1 and sigma 2 coincide on a dense subspace, you can take limits, it's justified, and you get equality at the whole space. So my standard example is that you cannot take a closed subspace, then you still have a restriction property, but no injective embedding here. And we have this situation quite often. I also recall the Fourier algebra is the set of all the Fourier transforms in the sense of measures. So these are bounded continuous functions arising as the Fourier transform of L1 function. Of course, if you're familiar with Lebesgue integration theory, you can say it's the integral transform applied to arbitrary L1 functions. It was also quite useful and important to realize that L1 intersected the Fourier algebra is a dense subspace of L1 and actually also of the Fourier algebra. The important statement which took us a while last time was to prove the Fourier inversion theorem, which was a consequence of the fundamental relationship of the Fourier transform. So you're saying this red formula 186 is valid, and then you specialize. You would like to pick up the value f at t, so you make the g hat such that it's concentrating, it's a Dirac sequence at t. Now, how can you do it? Well, by choosing the g in one of those spaces where everything works fine in such a way. So we take a triangular function, and here we make use that the Fourier transform of the triangular function still can be used to form a Dirac sequence, and that gives you f of t, and on the right-hand side, you get the version, the full integral, which exists if f hat is in L1. So you have this identity for both functions g and f in L1. You make appropriate choices, and if f and f hat are integrable, the limit is justified. We had a problem with the normalization. So up to this point, with completely elementary means, we can show that the Fourier transform on L1 is injective, and you have the inversion formula, but on f and L1 intersected FL1, but the normalization depends on your choice. So we have to use, for example, the properties of the Gauss functions, which I did not do here, to prove that it has integral 1 and it's Fourier invariant. This is something that you can find in the books. And if I find a way out of avoiding this, I will be happy. Now, the other choice that you can do is, instead of doing the Fourier inversion theorem, is to try to choose f equal g and to find that you can prove Closure Theorem. And that is stating that L2 is going into L2, while again on L1 intersected the Fourier algebra, you're proving isometry and then you take limits. So it's again a functional analytic principle to extend the isometry to the limit space, which is the Hilbert space L2 with the standard scalar product. We will not, we take an intuitive approach to L2 at the moment. We will see how to view L2 as a subspace of mild distributions again, just because I try to avoid Lebesgue integration theory, but it's of course possible, and then you have Placherel in full detail. Now, one of the main properties that will be useful later on is the invariance of the Siegel algebra is 0 under the Fourier transform. And for this, we need to first recall that the bounded measures can be convolved with the Fourier algebra, which we have done, observing that it's just multiplication on the Fourier transform side with the bounded functions mu hat. And we can control mu hat in the sup sense by the total mass of the measure. So this is no problem. Here we have the Cauchy, the Hilbert space setting. Just recall the most important estimate for Hilbert space and scalar products, which is given in this way, 199 at the moment, is the Cauchy-Schwarz inequality, which if you put f and g on the left-hand side, it just says, well, f divided by the norm of f in a scalar product with g over the norm of g is in terms of absolute values between -1 and +1, which is a good idea to allow you to define the angle between two elements in the Hilbert space L2, because every value between -1 and +1, it's the range of the cosine, can be taken. So we would say they are orthogonal if the scalar product is 0, which is, you would think this is 90 degrees, and that all that works, and that's why the Hilbert space is so useful. So this is an explanation of how we can do it. The next step was, or is to indicate that even if we have this nice inversion theorem on the smaller domain, this was the red octagon at the early beginning. If you have the Closure theorem, which is L2, which is larger and bigger, and you cannot write integrals anymore, we still have no clue at the moment how to get back from constant 1 to the Dirac delta. So the integral transform simply doesn't allow you to integrate constant 1 against this here. So I would say we are trying to explain now how to read inverse Fourier transform of constant 1. And if you think, I mean, this is an engineering terminology or notation now. If you think that this is meant to be going back from the frequency domain to the time domain, then you should get a function of t. Now, if you take the inversion formula literally, you take the constant function 1 as a function of s, which is the frequency domain. You say, I have to integrate that guy against e to the plus pi I. So I'm doing Fourier synthesis and integrate over this, which, I mean, 1 is not, you don't have to write it, means this integral. And what you expect is that this formula is undoing the Dirac, is undoing the forward Fourier transform. Now delta 0 goes to a constant 1 by the Fourier transform, so this should be the delta at 0. So Dirac measure at concentrated at 0. Now, usually I'm saying people are arguing that this integral is an oscillatory integral, so it's plausible that it gives you 0 everywhere except at t equals 0. And if you take t equals 0, you have constant 1 integrated is plus infinity. So yes, this looks like a Dirac delta, but it's absolute nonsense in the sense of mathematical precision. You should not use a pointwise argument, and also the normalization. Why should the integral over delta 0 be 1 or so? So please, whenever you see this symbol in engineering books from now on, please say, oh, this is the symbolic description of f to the -1, but we have to do it carefully and so on. Now, I was already referring to the Closure Theorem and want to recall a little bit the notation about these two algebras, which are quite important, which are obtained by localization. So if you give me a nice algebra, and so far we have only two of them, C0, continuous function with compact support, could be the A with the sup norm, or you take the Fourier algebra. Then you get a space which I call the Wiener amalgam space with local component A and global behavior L1. So that just means summability. What are you doing? You're taking a partition of unity which is bounded in A. So typically in our case, psi k is a collection of shifted elements which all have the same norm of one element in the Fourier algebra. Prototypical example, take the triangular function or a collection of trapezoidal functions. So if you have such a sum and if A is a Banach algebra, it's clear that you're talking about an absolutely convergent sum. So the sum of all these pieces added up in any way will be uniformly convergent, will be even convergent in the norm of A, and will give you an element of A, but pointwise it's giving you just F. So it's the subset of all those where this decomposition written in a naive way is not just a sum in the pointwise sense, but it's absolutely a norm convergence. Clearly the partial sums, the finite partial sums, will be also convergent in the sense of A, but even in the sense of the bigger of that algebra with the more sensitive norm. It's also clear that you would take that norm, that expression as a norm, and you have immediately the question whether this is independent of the partition of unity. And yes, you can do it. And the way how I was doing it was the atomic decomposition. Or we shouldn't say decomposition. It's like Lego. You're seeing a Lego building and you're not going for decomposing it, but rather thinking, well, could this be done from a collection of building blocks? There are many ways usually to build the same building from different bricks. And that's exactly what we have here. So you can say an atom is an element in A, which is supported in some ball at some center. And the radius, if this is a radius, is uniformly bounded. So all the atoms are the same size as the elements F psi k also, of course, of the size, such a thing. Then you're adding them up, and the point is, then you're getting the same space. So whereas here you're doing a specific decomposition, that's really a decomposition. You should say here, we're saying anything which has an atomic composition, which can be built in a certain way, will, if you then look at it and decompose it with a specific way, will be summable in this sense. And therefore, of course, you can switch from one BUPU to another, and you get many other properties from this atomic characterization. The main point was that assuming that you start with atoms which are allowed to have a big radius, that you can count the elements, how many psi k's are hit by such an atom. And the number is uniformly bounded, because even if you would shift the blue box to another position, the counting would be the same, because the area of the blue box is independent of the position. The area of the red dots is also independent of which points can be used. So, and therefore you can estimate one by the other. So the norm of each atom can be controlled by the ordinary norm for a given BUPU. And if you sum over all the atoms, you're getting a double sum and everything is fine. Of course, the proof shows that the infimum over all possible representations is a norm which is equivalent. Usually I call the sum of all these atoms, which is the A norms of these building blocks, the price of a representation. So admissible representation is a representation with this side condition that atoms are bounded by the box of fixed radius, and they're all in A. And this is the value, the cost of a representation is the total sum of the links of the A norms. Now, the value of a representation, or what is a good representation, is obtained by taking the infimum over all possible representations. We don't claim that there is a cheapest representation, but we can claim that you cannot get it arbitrarily cheap, because clearly you can estimate the A norm of H by the sum of the pieces. Therefore, the infimum is a positive number, and it's really a norm, and it's an equivalent norm to the one obtained by decomposition. So you are free to choose your partition of unity. And in the case of subnorm, you can even skip the continuity. So a natural way of describing the norm for C0, or actually L infinity if you want, is to take the supernorm over intervals from n to n plus 1, or in multidimensional over cubes. So in the two-dimensional case, for d equal 2, you just take a piece of paper with a squared pattern, and you take your landscape, which is like a mountain, and you make an upper Riemannian sum, or a kind of a Lego approximation from above, and then this is the norm. So even a tiny peak may result in a big local maximum, and that's why you're having various properties. Now, we were proving, or I was indicating all these possible properties. For example, you can dilate functions if the space A is dilation invariant also in these boxes, simply because dilation makes out of functions living in a box, functions living in a dilated or compressed box. But since this atomic representation theorem is always true for any radius, you can choose another radius. It's clear that changing the radius, of course, gives you a different norm and different constants, but it leaves the space invariant. So we have, if we start with C0 or with the Fourier algebra, all of them are translation invariant, modulation invariant, dilation invariant, and these properties are inherited by the new space. We also get completeness, so we have very nice spaces, and this will be used quite a bit. So the most important properties for now, if I think already of S0, which is the space with locally Fourier algebra global L1, or is that you can convolve with bounded measures. And the trick again is very simple. Any bounded measure is decomposed into local pieces. These elements by definition are local pieces. So what you have to do is to control these single pieces. So you convolve m psi I with f psi j, you look where it is, and you find that these are atoms. From this, you get the property that the approximate units are acting in a good way. This is also again true for C0. For the Fourier algebra, maybe it should be written up, but you compress it and you have this property. So approximate units are fine. Again, this gives you that the band-limited elements in this space are dense, but we know better because we have a lot of knowledge now. And the lemma 33, which I was shortly explaining, that small spaces are embedded densely into larger spaces, means that we have embedding is now applicable to this situation. So the small space, once more, is WFL1L1, so the space which behaves like the Fourier algebra locally, but with pieces absolutely summable, is inside what is called very often Wiener algebra, or the Siegel algebra found in the book of Hans Reiter. This is simply because we can control the supernorm of the Fourier transform of an L1 function by the L1 norm of the original function. So again, essentially, this dense embedding is a consequence of the Riemann-Lebesgue lemma. And because we have this duality, it means that everything which is bounded on the Wiener algebra is also bounded on S0. So we can say these measures, and this is justified because essentially the dual elements are locally measures glued together in a way which makes them uniformly bounded, the so-called translation bounded measures. They are also elements in the dual of S0. So in words, I would express this estimate by saying that translation bounded measures, well, this is how we will describe it later, are also mild distributions. The point of such a statement is, I mean, why do I worry about these things? Because the Wiener algebra, this function space, is nice. It allows the Fourier transform, but not the inverse Fourier transform. So we are going for something which is Fourier invariant. And if we interpret something which could be a Dirac comb in a moment, is in that space, it will be also viewed as a mild distribution, and as such, it has a Fourier transform. Now, because we have it here, I would like to mention that there is a partial converse to this. So later on, we will see that if a distribution, a mild distribution supported on a lattice, is essentially a sum of Dirac measures, it will be automatically also in this other space. So it will extend from the S0 space to the Wiener algebra. That's a different story, which takes more work. But it's easier to prove that a positive functional is automatically, it is the same to say it's a mild distribution or it's a functional on the Wiener algebra. So what is a positive functional? Of course, a functional that takes positive function into positive values. So if you take an ordinary positive non-negative function, g, you turn it into a measure, that a positive function gives you a positive measure. How can you characterize it? Well, exactly by this blue property. So we have a notion of positivity for functionals because we have positive elements in the range and in the space of test functions. Now, the claim that I would like to make is that if you have a positive element in S0 prime, so a positive mild distribution, then it's actually a translation bounded measure. So it can be extended from S0 to the Wiener algebra. The argument is relatively simple because what you have to do is to use the positivity that larger functions have larger values as under the functional. So you have an order of functions by saying, well, f1 is bigger than f2 in the pointwise sense if the difference is positive. So bigger functions will have bigger integrals. So what we have to do is to find that for every element that you would give me from our small space S0, I can find, from every element from the bigger space to which you want to extend the functional, I have to find an element from the smaller space which is dominating it. So it's kind of the fine properties of this Fourier algebra which are different, but globally, in terms of domination, it's easy to dominate every element from the Wiener algebra by an element from S0 prime. So how can we do it? Well, we just observe that there are functions of, maybe I should also produce a MATLAB plot for illustrating this, but you should think of phi being a trapezoidal function. A trapezoidal function is a convolution product of a small with a big rectangular function, and we can do it such that it's constant 1 on a ball of radius r around the center, and then by shifting it to a ball of any position, we get shifted trapezoidal functions which are reproducing all these functions f times psi k. So if I take a BUPU of size radius r, the support of f times psi k is inside the ball around the center, which is k, the lattice point, with radius r. So if I shift my trapezoidal function to this, then of course I have to make the amplitude of the phi appropriate. So I will take the maximum of this f psi k and shift my trapezoidal function. But we know, and that's the definition of the Wiener algebra, that this sum is absolutely convergent. So we take all these trapezoidal functions, we add them up, and we get a function which is bigger than the absolute value of x, and we call that function h of x. I think the absolute value here should be put on the outside. So sorry, it should be absolute value of tk phi minus f and not inside. Now, by the positivity of the functional, we can control the value of sigma by this here, but this is just the sum of this f psi k is just the Wiener norm of f. So up to the norm that this trapezoidal function, which is an auxiliary guy, has, we can control the functional norm on the dual, in the dual of the Wiener algebra by the norm in the dual of S0, so which is this. So the size of the constant is telling us how to estimate this. So yes, mild distributions are a little bit more general, but they will this will buy us the invariance under the Fourier transform. Here, if you have time to read it, I'm giving you a little bit of hint to the literature. So this space was a so-called Siegel algebra. This S is referring to Irving Siegel, And Hans Reiter, in his book, who you owned, and also lecture notes, was doing a lot about general Siegel algebras. It appears now, meanwhile, that this specific Siegel algebra has a wide range of applications, and I'm keeping to discover more and more as time passes on. Some people, especially in the new edition of Reiter's book, call it five-dimensional algebra, which is, of course, honorable for me. The Wiener algebra is among, if you choose C0, you find out that among all the Siegel algebras which allow pointwise multiplications with C0 elements, you get the Wiener algebra. And so I was interested to find whether there is a smallest element in all the function algebras, Siegel algebras, which are invariant on the multiplication with the Fourier algebra to make the situation more symmetric. And that was exactly WFL1L1. So it was a certain minimality property, which at the very beginning allowed to prove many properties. Now, in this course, I'm trying to use concrete facts about the real line, trying to put everything in a setting which is generalizable to locally compact abelian groups. I don't go into these details, but I would like to mention that one of our goals, the next goal, is to prove Poisson's formula. And Poisson's formula is having a range of validity, which is the W intersected the Fourier transform. So this is which I'm representing nowadays as my square. So clearly the square is containing the nice little circle, which I call a 0. But for the proof of the Poisson formula, we need this property. So it's not true anymore for the L1 intersected FL1, but you have to restrict further. And because of all these technical conditions, it's at the end we will see it's better to use just a 0 and a dual space with the L2 in the middle. Now, it was really an important theorem that we did last time to prove that we have Fourier invariance of this space, and because it's embedded in the Wiener algebra, it also means, of course, that we are inside this range. So whenever we are, or when we will prove Poisson's formula, then we will also have it for a 0, but that's just a consequence. Now, I don't, of course, repeat the technical part, but really come to the beginning of the new material, unfortunately, only now. We are having, but I hope you are having a better perspective now. You're having a definition of the Fourier transform. I call it for a moment the extended Fourier transform, and we will really verify that it's an extension of the original one by saying, you give me a functional, a mild distribution, and you want to know what the Fourier transform is, just take the original function and apply it to f hat. So in reality, this is again a form of adjointness relation. Instead of applying an operator, which we call ft, and we should call it ft adjoint to sigma, we apply the sigma to the function f under the ordinary Fourier transform. But because of the fundamental relationship, this is not only a tricky way to define some kind of Fourier transform, but really to extend it. So this is compatible with the formula. Now, one important step to show that the Dirac comp, and we will use a lot these Dirac comps now, is in the space of mild distribution. Actually, in the dual of the Wiener algebra, we have to recall this situation. So what is the most general Dirac comp in multidimensional signal processing? We call it lattice lambda, and it's obtained by distorting the standard lattice ZD by some non-singular matrix. Of course, it should be a D by D matrix, not N by N. Now, why is this a translation-bounded measure? And the answer is, again, the same picture. Now you have a little bit changed situations. We're placing some figure or some in 2D now, some part of the fundamental domain around each lattice points. And if you want to compare the number of points in an area of some circle, you will find that this is a limited number that will allow you to control the action of this Dirac measure. So this Dirac comb. Okay, sorry, I didn't write it here. Yeah, here it is. Yeah. So the Dirac comb over lambda is just the sum of the Dirac measures with sitting at all the lattice points. So at each of those centers of the lattice point, you put the Dirac. The claim is that this is a linear functional. And the answer is quite simple. We only have to apply it to the elements which are atoms. So if you give me an atom, it will be concentrated in some blue ball that we had before around some point. You're applying all these Dirac measures, but only finitely many of them are applicable. But we can control the number independent of the atom, of course. So it's just depending on the configuration space of what the lattice is. If you give me a lattice, I will figure out, and the radius of your atoms, I will figure out what that constant is by a counting argument. But we also know that we can control the sup norm of the atoms by the Fourier algebra norm of the atoms. And therefore, we have a control of the action of the linear functional on each of the atoms. And by summing up, we are having the sum of this here. And of course, that's telling you we can control the action, this Dirac comb applied to H. It should be H, F here, sorry, that was a copy. The F here should be, and then you can have the estimate. So just because I want to illustrate this, here I'm telling you how to realize in 1D the number of points that you have in an interval. Okay, so here clearly it should be x minus capital R to x plus capital R. And I'm moving my interval, and you count how many points of a lattice you have. Now in 1D, a lattice is simply just a dilated version of the integers. And you will see that the number is varying. It's either 2 or 3 in my example, but it's uniformly bounded, and that's the main point of the estimate. Okay, again, I'm coming back to my picture book. We have all the spaces more or less with standard colors meanwhile or so, except that now I'm emphasizing the Wiener Algebra. So C0 L1 is something which is, of course, it's inside the green area. It's, of course, consisting of continuous functions. Locally, and that's in the middle, it's horizontal line. So locally, it's the maximum norm. Globally, it's more like L1. So that's why we have this side here. But it's not inside of the Fourier algebra. It looks, of course, like there were very few examples. But yes, you cannot conclude from continuity only with compact support that you're inside the Fourier algebra. That's quite clear. But we will see that S0 is much more beautiful. Now, the dual spaces, because the circle is inside this intersection of Wiener with the Fourier transform. Sorry, when the Wiener algebra, sorry, S0 is inside the yellow object, we have the opposite inclusion of dual spaces. I don't explain the details, but this is the translation bounded measure. So locally measures globally sup norm boundedness. So it's this object which I use to depict this. So locally it's a bit like the measures, so which is like L1, whereas S0 is the reflection of this here along the circle, which is here depicted by magenta. So that we will see later, we work with a Banach-Gelfand triple S0, L2, S0 prime. That avoids all these complications that you always have to make elements from a dense subspace. So S0 will be the dense common subspace for all the things that we will do in the near future. So I think I will do the following thing in a little, in much more detail later on, but I would like to indicate that these amalgam norms, which are introduced with BUPUs, because I think this is the more natural way, can also be controlled or described by continuous norm. So whereas a BUPU is cutting out pieces and doing this, we can also do this in a continuous fashion. And we'll also see with the spectrogram, if you apply the spectrogram, you see that you get actually a continuous decomposition, localization. So if we take a trapezoidal function, say, and we move it and we measure it in the B norm, which is any of the norms that we have already, then we would call this the control function of f. That's the signal that we analyze, can be a distribution, a measure, or a more general. So it could be mild distribution, for example, localized by something which is fine enough. So it would be in a mild distribution, that would be an element from the Fourier algebra. Then you're measuring this in a certain way. And then you're saying this is a control function. Now the L1 behavior is a global behavior, can be replaced by an integral norm. So whenever you are looking into the literature and you're seeing that you have a space which is an amalgam space of local behavior A and global behavior L1, it refers to this kind of description. And one has to work a little bit to find out that the finiteness of the control expression is equivalent to the BUPU representation. So you get the same space, but in a continuous way. Now, why bother about such a thing? Well, the continuous norm is clearly completely translation invariant. So if you shift a function, it means that you're shifting the control function. If you take the Fourier algebra norm and then the integral, everything is exactly translation invariant. It's also modulation invariant. So it's a very nice thing to have compared to the BUPU, where things which are located in one box after shifting may be split into pieces. So it's a nice equivalent norm. However, if you would think of an atomic decomposition, it would be a continuous overlapping of the pieces. And yes, you can write it as a continuous vector valued integral, but because if you change now from L1 to L2, you cannot get this same intuitive embedding property like you have it with little L1 and little L2. So absolutely summable discrete sequences are also square summable. That's quite obvious. But with L1 and L2, you don't have such things. So I think it's much easier to think of this. Maybe before concluding, before the break, if you do this description, I call this a continuous selective description. So everything that can be localized, so which is locally in the space A here, can be controlled. And then you take by continuous condition those which are okay for you. The atomic representation is what I call a discrete synthetic description. So you're putting building blocks. And if you think of the old way how people were making highways, you would say there's a block of concrete, like 5 or 10 meters, then there's another block, and altogether you get the highway. Now, if you take the continuous way of putting this together, it's like the asphalt machine, which produces 10 kilometers of continuous road by continuously putting material and moving in the same way. So yes, these vector valued integrals can be understood as putting little pieces, but taking a limit of BUPUs, which are finer and finer. I think this is a technical trick, which is kind of with this asphalt machine maybe better understood, but I leave it out to you. Now in the text, you will find several properties of the Wiener algebra, also picture how it's related to the other spaces that we had at this moment. Another picture, but I don't have to go through these details. We know better now. And I think I will go into the break. Yeah, maybe I stop here with a nice picture of a BUPU and this localized reconstruction. Thank you for the moment.